All right, good morning, everybody. Um, I was told by my other students that you haven't received your FRQ for test 3 yet, but we were done grading it last Monday evening. So at least I finished it in the afternoon. But the thing is that there's only one person allowed to upload everything in CASA. So our lead TA is, I guess, still working on it. So kindly wait for it in the coming days, and you'll be able to see it. And then uh, once you gain access to it, please take a look at it and then um, review it. And then if you think you should have gotten more points for a particular problem, then let me know. I'll let you know the deadline for regrading requests. But yeah, some few comments that I have. I graded 97 papers. I'm not sure if or who among you were among those that I graded, but major concern that I had is some students um, omitted some significant parts of the solution. I mean, you can skip some of the arithmetic steps that you could have done mentally, but there are some points or some parts of the solution that are very important and are not that simple that should be included on paper. For instance, there's a partial fraction decomposition problem. So say you have a polynomial over a polynomial, and then you do a partial fraction decomposition. So theoretically, you should write the solution this way. So you say, oh, this big fraction is equal to a, say, x squared plus 3 plus d over, say, x minus 2. Something like this, right? And then you will show your solution for a, b, and d. But that's not what a lot of students did. Out of the 97, probably 10 to 15 students did it this way. So they start with a given expression, and then they say, oh, this is equal to, say, 2x minus 1 over x squared plus 3 plus, say, 3 over x minus 2 dx. And then they went ahead to find the integral plus c, right? Now, the thing is, I want to see how are you able to calculate this decomposition just coming out from the big fraction. Unless you are very good at mental math and you were able to compute the decomposition in your head and come up with this one, right? So in that case, well, in those cases, I gave them the benefit of the doubt and just thought, all right, they did the solution on their paper. Or they might be geniuses that they can do the calculations on top of their head. But I suggest you include all the solutions because not all the graders will think that way. They might think you copied the coefficient somewhere or you found it on the net or something like that. In an exam wherein you are not doing it in person, it's easy to assume that you did something wrong. But yeah, I just gave them the benefit of the doubt and thought, okay, probably they did it on a scratch paper or something, right? So yeah, but I hope next time you include everything, right? All the significant like this one, okay? Now another thing is for trig saw. So they were given a radical here. So yeah, let's just call your function f of x dx, for instance. And then you use trig sub. And then after a series of steps, which they include rigorously in the solution, then they come up with, say, cosine theta plus c, right? Which is fine. They included everything up to this point. And remember, how do we revert to the original variable x? To get back to the original variable x, what we did before was to draw a triangle and say, oh, in this triangle, let's pretend this is the right angle and theta is based on the substitution statement, we can determine what are the measurements of the legs and what is the hypotenuse. And based off of that and the SOHCAHTOA relations, we can compute what cosine of theta is. But I don't know how, but some students did it this way. So they say, okay, cosine is, for instance, this is arctan of x over 3 plus c. Because basically what they did is they they probably have this trigonometric sub. Let x be equal to 3 tangent theta. Then they did x over 3 equals tan theta. And then theta is arctan of x over 3. Some of my students from the other lab told me that Professor Almus told you not to do this. So I don't think you did this thing in the exam. Though this might be construed to be something correct, right? So you found the value for theta by using the inverse arctan function or the inverse tan function, which is fine from a theoretical point of view. But the solution that we're expecting is much more elegant than this, right? So we should have gotten something like 3 plus x squared plus c all over something here, right? So over hypotenuse or something like that. But what puzzled me or what surprised me is that students did something like this. Probably their lecturers allowed them to do that. But I was just puzzled. How were they able to come up, to jump from this step up to this step? Unless they were given a very fancy trigonometric identity that involves cosine and arctangent or something of that sort. If this was an arccos, then I'll understand because cosine is the inverse of arccos. But it's a cosine followed by an arctan. We don't usually teach that kind of identity. So yeah, that bothered me a little bit because I don't think those identities were taught in algebra or trigonometry unless they were specifically given in the lecture. But I hope you guys didn't do that. Hopefully you did it this way using the usual triangle and so on, right? That's much easier. That's more intuitive than this fancy identity here. Nothing is wrong with that if you were specifically told to memorize or you found an identity like this. But yeah, but some graders will be a bit suspicious about how you come up with the answer. All right. So lesson there is please include in your solutions all the necessary details or all the salient points, everything that cannot be done mentally. So please include them. That will be that will be that will work in your advantage in two ways. Number one, you can trace your solution better because you have all the steps written clearly. And number two, you can get partial credits easier if you got all the details of your solution and you just mess up at the end of your solution, right? Okay, now that's it for the exam. So again, please watch out for the FRQ part to be available in CASA. Now, I guess last time we were talking about sequences, so let's go back to our discussion then. Have you tried some of the quizzes already? So it's just quite odd because I guess it's seldom that somebody sends a question in this class. So if you have some questions or you already encountered some hard ones, please let me know in the chat. So I'll be happy to walk you through them. But while you're composing your questions, I guess we stopped here last time. We're looking at whether n over n plus 2 raised to the n is a convergent sequence, right? So we say a sequence is convergent if it has a finite limit. And if it doesn't, then we call it a divergent sequence. And there are several tools at our employ for determining what the limit of a sequence is. I guess last time I started using sort of the Hitch theorem, which tells us that the limit of a sequence is basically hinging on or is equal to the limit of the real valued version of that sequence, right? So here, I guess that's what I started doing. Did anybody get to finish the solution? Yeah, kindly let me know in the chat if you have an answer to this. But yeah, so our first attempt was to write the first few terms and see if we can conclude something. But that is a bit difficult because we cannot discern a certain pattern by just looking at the first few terms of the sequence. So we'll go to some analytical tools and we say, okay, I'm going to take the limit of my n term. Now, if we do so, we know that n over n plus 2 will go to 1. It is not exactly 1, but it is something approaching 1, right? And then we have an exponent n, so this is something approaching 1 raised to infinity. And if you remember from Cal 1, it's an indeterminate form, right? So being indeterminate tells us, oh, I might need to use L'Hopital's rule. But before we will be able to use L'Hopital's rule, I need to get rid of the exponent. Because remember, L'Hopital's rule only work when you have infinity over infinity or 0 over 0. And here we have an indeterminate form with an exponent. And if you remember, what we did there is to first get rid of exponents, right? So the trick here is to rename your function. Let's call it y. And then we take the limit of both sides. But before taking the limit, right? But just remember that we are looking for the limit of y, right? Because y is this, we're computing the limit of y. But what I did here as preliminary step is to take the natural log of both sides. So I take ln of y. That's why I got that on the right. And then I took the ln here. So I would have gotten ln of x over x plus 2 raised to the x. But I used loss of logarithm, which allows us to use this exponent as a coefficient. So that x will be in front of the ln. That's how I got the right-hand side. And now I'm trying to take the limit of both sides as x approaches infinity. But keep in mind that we are solving here limit of L and Y. But the original problem is to take the limit of Y, right? So that means if we will be able to solve this guy, then there's an extra step to be done. Because here, the whatever limit we get here is the limit of L and Y. So to get the limit of Y, we need to use this number as an exponent to E, right? So let's just keep that in mind. So let's go here. You try direct substitution. X goes to infinity. X over x plus 1 goes to 1. So the second factor goes to ln of 1. ln of 1 is 0, right? So that means it's infinity times 0. It's an indeterminate form. So if we have an indeterminate form, we need to write it in terms of 0 over 0 or infinity over infinity for L'Hopital's rule to apply, right? So if you remember from Cal 1, we need to decide or to choose one of the factors and put the reciprocal of that factor in the denominator, right? So I suggest you keep the more complicated function on the numerator. In this case, the natural log is much more complicated than x. So I'll leave the natural log on top. And then I'll put the reciprocal of the other factor in the denominator. Okay, and I did that so that if I simplify this, I'll go back to the original problem. So what we did here is all but a rearrangement of the factors. But why do I want this arrangement? Well, in this arrangement, the numerator goes to 0, right? Because still it's ln of 1 or approaching ln 1. So this will approach as 0. But the denominator, as x approaches infinity, will go to 0, right? And now we have the form 0 over 0, which is indeterminate still. But the nice thing is we can use L'Hopital's rule now, right? So L'Hopital's rule tells us that the limit of this indeterminate form is equal to the limit of the ratio of the derivatives. So we take the derivative of the top. Right? So that's 1 over x plus 2 times the derivative of the inside. Remember, I need to apply the chain rule here. So I need to differentiate x over x plus 2. But to do that, I need the quotient rule. So I'll have x plus 2 squared, low derivative of the high, which is just 1, minus high derivative of the low, which is also 1. So I have that. And then the derivative of 1 over x is negative 1 over x squared. And we take the limit as x approaches infinity. Okay, I hope this is clear. So if not, then you need to recall these techniques from Cal 1. Okay, now let's simplify this expression. So as x approaches infinity, oh, this is minus 1 over x squared. I can write it as minus x squared. And then the first factor here can be simplified as x plus 2 over x times this, this can be simplified into x over x plus 2 quantity squared. And then we can cancel some common factors. I'll cancel the x's. I'll cancel the x plus 2 above with one of the x plus 2's in the denominator. So essentially we'll have minus x squared all over x plus 2 quantity squared as x approaches infinity. All right. And then if you see here, the numerator is degree 2. The denominator will also be degree 2 once you expand this product. So basically it will be the ratio of the coefficients of x squared. The numerator has coefficient negative 1 for x squared. The denominator upon expansion will have x squared as leading term, right? And the coefficient there would be 1. So essentially this would be negative 1. But hold on, this is the limit of ln y. So we now go back to the limit of y, which is this guy. Okay. Therefore, we can say that the limit of our n term as n approaches infinity is e to the negative 1, right? Remember, this negative 1 is the limit of ln y, so we're going to use it as an exponent for e. And so this limit turns out to be convergent, and it converges to e to the minus 1. Okay, guys, is that clear? I feel some hesitancy there, Christina. So probably at least the process hopefully makes sense. You just to remember, you just need to remember the things that you have learned in Cal 1 and refresh a little bit on that so you can apply them in these topics, right? I don't know what's happening with the internet connection here at the university. It looks like I'm cutting in and out of the session because there's some momentary disconnection of my internet connection. So kindly bear with me for the next 30 or so minutes. Okay, now there's a couple of questions in the chat. Let's try, okay. Let's number it number 9. You have the sequence ln of n plus 10 all over n. And yeah, we'll try to see if this can. So we'll take the limit of the n term as n approaches infinity. If you try to imagine what happens as n becomes very, very large, the numerator will be ln of a very large number, right? And ln of a very large number is still a very large number. So the numerator goes to infinity, as well as the denominator. This will also go to infinity, right? As n goes to infinity. So the thing here is we have an indeterminate form. But if you will use L'Hopital's rule, I suggest you do a change of variable, albeit a superficial one or a seemingly superficial one, because L'Hopital's rule only apply for functions of real variables. They will not technically. So this to circumvent that limitation of L'Hopital's rule, I'll use the Hitch theorem that tells me that the limit of the sequence is the same as the limit of its real valued counterpart. So now the change in the variable here signifies I am allowing x to be any real number that goes to infinity, okay? Rather than just natural numbers. And now I can do L'Hopital's rule here, because here, as we have said earlier, we have the indeterminate form infinity over infinity. I'll apply L'Hopital's rule, which tells us that the limit of the quotient is, as long as it is an indeterminate form, infinity over infinity or 0 over 0, is equal to the ratio of, is equal to the limit of the ratio of the derivatives. So we take the derivative of the numerator, ln of x plus 1 has derivative 1 over x plus 10. And then the denominator has derivative 1, right? And if you simplify, this is just the limit of 1 over x plus 10 as x approaches infinity. Numerator is a quotient 1. The denominator, x plus 10, goes to infinity when x becomes very, very large. So you have 1 divided by a very huge number, that will go to 0. So we say, therefore, the sequence converges to 0. All right. Yeah, great, Kevin. Yeah, some problems really look intimidating, but once you put your hands to it, to be easy. Especially if you do all the if you include all the details in your analysis. So some questions are designed to throw you off or to intimidate you, but once you dissect it to their barest essentials, then you will see that they are not that hard. Now let me go to Christina's question. I think we have a similar one to this, though I'm not sure. But let's see, you have n minus 5 to the negative 1 to the n all over n, right? Then we want to see what happens. Okay, so here we can analyze the n term. So I'll just copy the n term here. So n minus 5 to the 1, negative 1 to the n, all over n. I can do the division term by term, right? So whenever the denominator is a monomial, you can do term by term division. Actually, not just when it is a monomial, but you can separate the numerators into fractions with denominator equal to the common denominator. This is just doing addition of fractions in reverse. So you'll have n over n minus 5 times negative 1 to the n all over n. So this would be 1 minus 5 times negative 1 to the n all over n, right? But what happens here as n goes to infinity? Well, as n goes to infinity, a sub n will go to what? Okay, you have a 1 here. 1 goes to 1. It's not involved there. So when n becomes large, the first factor or the first term remains to be 1. But let's analyze the second term. Well, the second term involves negative 1 to the power n. So we know the effect of factor negative 1 to the power n is basically making it alternate in sign, right? So it will go to plus, it will start with negative 1, positive 1, and so on. So basically the numerator here is actually either plus or minus 5. Agree? So it doesn't matter how n becomes large. The numerator needs to be either positive 5 or negative 5, right? But there's a denominator n, but n goes to infinity. So we have either plus or minus 5 divided by n. What do you think will happen when n is large? Anybody? What happens if we have plus or minus 5 divided by n as n grows very large? Come on, guys. What do you think will happen? Yeah, Kevin, yeah, the numerator will have the pattern plus or minus 5, right? So yeah, I hope we're clear on that. The numerator is either plus or minus 5, right? But what happens when I divide either positive or negative 5 by a very large number? Do you agree that this quotient will just go to 0? I hope you do agree, right? Because the numerator, whatever happens to n, the numerator is just either positive 5 or negative 5. If you divide positive 5 and negative 5 by a very huge number n, then it will go to 0. So basically here, our expression an will go to 1 minus 0 as n approaches infinity. But obviously 1 minus 0 is equal to 1. Yeah, no worries, Christina. But I hope that solution now, or the explanation now goes back to your memories. Right? So for problem 10, sequence converges to 1. So sometimes you need to manipulate the given expression in order to see what happens. All right. Now let's try some more examples. There are some functions that we cannot apply the H theorem to, in the sense that these functions doesn't have a real valued analog, right? Remember in the previous examples, we hitched on the property of the limits of real valued functions to find the limit of our sequences. But sometimes we cannot do that because of how the functions involved in the definition of the limits were given. So for instance, our sequence is say 2n factorial over n plus 2 factorial. Oops. Do you guys remember how factorials are defined? Now, at least for us, factorials are only defined for natural numbers, right? And factorial is the product of the first n natural numbers. So you can think of n factorial as n times n minus 1 times n minus 2 times n minus 3 until you reach 3 times 2 times 1, right? But yeah, and you imagine why we cannot translate it into a real valued function, because it works by taking a discrete step back to get the next factor. So for factorials, we cannot do the same trick as what we did for the other indeterminate forms. But usually it's easier because we can do the analysis here by looking at how these factorials are defined. So for instance, here, you get your n term like this. Now expand the factorials. So just be careful with the notations here. You see 2n factorial. 2 is outside the factorial symbol because for another term to be inside a factorial, there should be an enclosing parentheses. So that considered, that means in the numerator, only n is inside a factorial, right? So you can copy the 2 times n factorial, but by definition, n factorial is just n times n minus 1 times n minus 2. You go decreasing until you reach 3 times 2 times 1. So this is our expansion for n factorial. Okay. Now for the bottom, or the denominator, you have n plus 2 factorial. So notice the grouping symbol there. It means that n plus 2 is the one inside the factorial. So that means it would be the product of the first n plus 2 natural numbers. So it is n plus 2. Then you take one step back times n plus 1. Another step back, you'll get n times n minus 1 times n minus 2 until you reach 3 times 2 times 1. That's the expansion of n plus 2 factorial, right? And the nice thing about factorials, you can cancel a lot of factors, right? Actually here, beginning from n until 1, you can cancel them by those factors in the denominator. So we'll be left with 2 on top divided by n plus 2 times n plus 1, right? And what will happen as n goes to infinity? So you have a constant 2 here. That's a mainstay. So all of the terms in our sequence will have 2 in the numerator, but their denominator will vary. It would be n plus 2 times n plus 1. But as n goes to infinity, the denominator grows very, very fast, right? So the denominator is also a huge number, or sorry, is a huge number. So here we have 2 divided by a huge number, and 2 divided by a large number will become eventually 0, or it will approach 0. All right. So here we conclude that the sequence converges to 0. Okay, is that good? Okay, now staying on factorials, let's try this one. How about, say, n factorial over n to the power n? What do you think will happen? Will it converge or diverge? Any guesses? Okay, Christina, you're correct, but why say so? Why do you think it will converge to 0? Exactly. The bottom grows faster than the numerator, which provides us, or which gives us, another way of checking whether a sequence is convergent or not. You can just compare the rates at which the numerator and the denominator are. If the denominator grows faster than the numerator, then the sequence converges to 0. If the numerator grows faster than the denominator, then it will diverge because the terms in the sequence will increase indefinitely, right? But why are you sure that n factorial, that n to the n grows faster than n factorial? Unless you were already told that in the lecture. But why do you think n to the n is larger, or it grows faster than n factorial? Okay, that's fine. I thought it would be a surprise or a good point of discussion, but you already had it in the notes. But anyway, for those who missed it in the notes, probably what was done there is to do the expansion. And you see, you have a sort of intimidating term expression here, n factorial over n to the n. But once you analyze it to its barest essentials, you will see that, oh, the analysis is not that hard, right? It's just it will just require you to put the work in it. So for instance, n factorial, right? I can expand it as n times n minus 1 times n minus 2 until you reach 3 times 2 times 1, right? And then the denominator is n to the power n. And remember, n is a natural number, so it's just n multiplied to itself n times, right? So this is done n times. And then in the numerator, how many factors do we have? We also have n factors, right? Because n factorial is the product of the first n natural numbers. So if you count how many factors we have on top, we also have n factors, right? Now we do the comparison as Kevin. Now compare the first two factors, or the first factor in the numerator and in the denominator. It's basically a tie. Next up, n minus 1 versus n, denominator wins. N minus 2 versus n, denominator still wins. And that will happen all throughout. So it means all but the first factor in the numerator is smaller than the corresponding factor in the denominator. So that tells us that the denominator grows a lot faster than the numerator, especially when n approaches infinity, right? So that means this goes to 0 as n goes to infinity. So the sequence converges to 0. All right. And then going back to Christina's suggestion earlier, she's right that when the bottom grows faster, the sequence will converge to 0. And as I mentioned earlier, when the numerator grows faster, then the sequence would be divergent. Well, probably this will help. I'll call it the hierarchy of rates of change. This is not an exhaustive list, but probably 4 of the most common functions that we will encounter. The slowest to increase, this is asymptotics as n approaches infinity. The function with the lowest growth, at least that will be in this list, will be the logarithms. They grow the slowest. So this list is slowest to fastest, right? Following logarithms are powers, x to the p, or sorry, n to the p. So polynomial powers will increase faster than logarithms, and then polynomials are followed by factorials. So n factorial increases faster than n to any power. So let's say n squared, n cubed, n to the fourth, n factorial beats them all. And of course, n factorial will indeed beat logarithm n, the logarithm of n to the base p a lot more. Okay, and then on top of the list would be n to the power n. N to the power n beats n factorial, as we have seen earlier. So n factorial beats all 3 previous functions. So I guess this will make your analysis much easier, right? Now, for instance, how do we use this? Let's try example 13. Say we have the sequence ln n over n cubed. Okay, so you can say solution 1. Yeah, you can say n cubed grows a lot faster than ln n, right? Following our hierarchy, logarithms such as ln is on the dead bottom of the hierarchy, followed by a polynomial, n to the p, or for our case, n cubed. So this will work for any positive p and any positive base b, right? So that means ln n over n cubed converges to 0. Now in the exam, I won't recommend that you just say, oh, ln n over n cubed converges to 0. We need a reason why you come up with that conclusion. And I guess this one is sufficient enough, saying that n cubed grows a lot faster than ln, or the natural log. And this would be sufficient proof. Okay? Now, if you don't buy into this argument, or you just forgot the hierarchy, you can do it in the long way. Alternative solution 2. You can be more analytic or more computational. So we take the limit of ln n over n cubed as n approaches infinity. If you do a mental analysis, ln of infinity will go to infinity. So top goes to infinity. As n goes to infinity, n cubed will also get to infinity. So we know in our heads that ln n over n cubed will possess an indeterminate form, infinity over infinity. But remember, how do we resolve indeterminate forms such as infinity over infinity? We use L'Hopital's. And L'Hopital's rule only work for a real valued function. And hence, I will need to change the variable. So here, n stands for natural numbers. I'll change it to x, signifying that the domain is now expanded to the set of real numbers except 0, or to all positive real numbers, because we're taking the limit as x approaches infinity. Our mental analysis earlier told us this is going to be infinity over infinity, which is fine because I can use L'Hopital's rule now. So derivative of ln x is 1 over x. Derivative of x cubed is 3x squared. So I hope you guys now are refreshed with L'Hopital's rule. So if you simplify this, you'll get 1 over 3x cubed as x approaches infinity. All right. And this will just go to 0 as x goes to infinity. And so the sequence converges to 0. All right. So you pick your method, but make sure to include all necessary explanations in your method, right? So if you choose the shorter and more intuitive one, solution number 1, then put a phrase or a sentence saying to some effect that the denominator grows a lot faster than the natural log, right? So you were able to say, oh, the sequence will go to 0. Or you can be more analytic and computational and use L'Hopital's rule here. Okay, is that clear? Okay, let me try some more problems. Okay, let's try another one. I don't know if we have answered already a problem like this, but this is a common question I got this from my previous lab. I also got it from the CASA tutoring that I'm holding every Tuesday and Thursday, 6 to 7 p.m. Shameless plug there. But I don't know if somebody already asked this in this class, say n squared plus 1 minus ln of n plus 4, or something similar to this. But anyway, I'll just go ahead and solve this one. So these are logarithms. So probably the Hitch theorem will allow us to do an analysis of this using limits. So let's try that. So I'll take the limit of the n term as n approaches infinity. Let's do a mental analysis. N squared plus 1 will go to infinity. So ln of infinity goes to infinity. Here, n plus 4 also goes to infinity. Ln n will go to infinity, right? They both go to infinity, so it's an indeterminate form, infinity minus infinity, right? So, but before going there, I can try to apply some properties in order to remove the infinity minus infinity. Try some tricks, maybe some algebraic manipulation, or perhaps rationalizing the numerator or the denominator whenever there are square roots. But here you have logarithm, so let's take advantage of loss of logarithm. I guess that's what you are suggesting, Kevin. You're correct. So remember, if you're subtracting 2 logarithms of the same base, you can put them inside a single log, but divide them. Minuend goes on top, argument of the subtrahend goes in the bottom, and take the limit as n approaches infinity. This might seem awkward because here I'm using loss of logarithm in reverse, right? So you have ln of a quotient, that is the difference of the ln's. Now, guess here we can appeal to the last theorem shown in the lecture, or in the textbook, that okay, the limit of the ln of a sequence is the limit of is the ln of the limit, right? So you can say, okay, this is equal to the ln of whatever the limit of the sequence is. So you can skip this step. I'm just showing it for the sake of completion or details, right? But n squared plus 1 over n plus 4, this goes to infinity, right? Because the degree of the numerator is 2, degree of the denominator is 1, numerator wins, so that means this go to infinity. And ln of infinity, or ln of a large number, goes to a large number. So basically this is infinite. So you can say here, so the sequence diverges. It diverges because we were not able to find a finite limit. So essentially, if you will write down the elements of the sequence, they will grow indefinitely large. And so that's why we say it's divergent. All right. Okay, there's one sort of Kevin, you can do, yeah, you can do L'Hopital's. So, but you will get, if you apply L'Hopital's here, you'll get you'll get infinity as your limit. So yeah, but if you do L'Hopital's, you'll come up with the same conclusion. Because I guess you need, you'll have L'Hopital's, you have 2n over 1, limit of 2n as n approaches infinity, so infinity, ln of infinity. Yeah, I think I took a shortcut there. Okay. Now, here's a tricky one. 3 plus 1 raised to n. What do you think happens to this sequence as n goes large? Do you think it will converge, it will diverge, or you'll need to use computational tools to determine its behavior? What do you think? No ideas? You don't want to guess? Well, yeah, you can do that, Kevin. But some students thought that, oh, this is an indeterminate form, because as n approaches infinity, they see that, okay, I'll have one, they'll say, oh, this is 1 raised to infinity, which is indeterminate, right? The same indeterminate form that we saw in our ln example earlier, right? The example, our first example for today. But they would be mistaken, because what's the difference? In that example, let's go back there. Yeah, in this example, though we have 1 raised to infinity, this 1 is not really exactly 1, but it is something that approaches 1. Because where did this 1 came from? This came from x over x plus 2, and obviously, x over x plus 2 is equal to 1. It is something close to 1, but not equal to 1. All right. So basically, though we wrote 1 here, we meant something approaching 1 raised to infinity indeterminate, right? But that's not the case with our instant problem, because our problem now has an exact 1 raised to the power n. So there would be no indeterminate form because this one here is really 1. It's not pretending to be 1. It's not approaching 1, but it is exactly 1. So maybe listing the elements will help us here. So when n is equal to 1, what happens? When n is 1, we get 4, right? 3 plus 1. If n is 2, we get 3 plus 1 squared, or 3 plus 1, still 4. When n is 3, we get 3 plus 1 cubed, which is still 4, and so on. So what does the pattern tells us? This will just go to 4. All right. So the sequence is just a long string of 4s. So if you have a long string of 4s, what is the limit? Or what happens at the tail end, quotations, of the sequence? Yeah, exactly, Christina. The sequence converges to 4. Because you just have a bunch of 4s, and remember, the limit of a sequence is what happens towards the end, or when n becomes large. It doesn't matter how large n becomes, right? Because even n is 10 million, if n is a trillion, that term will still be 4, right? Because you just have an infinite list of 4. So here we can say sequence converges to 4. All right. So and I guess this is a good place to stop. So any quick questions, clarifications, violent reactions? All clear for now? With a possible exception that you might need to go back to Cal 1, some of the techniques like L'Hopital's rules and limits at infinity. Kevin, will I teach Cal 3 next semester? No, because I'm planning to graduate this spring, so I'll be leaving the university. But I have never taught Cal 3 here in UH. I already taught all calculus classes back in my university in the Philippines, but Cal 3 here I haven't had a chance. But yeah, but I'll still be teaching even if I graduate. So probably next semester I'll be teaching, but in the Philippines. But you can follow my website. If I'll be teaching Calculus 3 there, or our version there of Calculus 3, I might upload some materials in my website as well. So feel free to access my website and see what materials I came up there. So I'll make all my materials available to everybody. And our language of instruction there is Filipino, so is English. So yeah, you'll be able to follow if I upload some of my teaching materials or my teaching videos. All right. Okay, so let's call it a day here. Thank you everybody for coming today. So let's see each other again on Friday, right? Hopefully we'll start with section 9.3, unless you'll have some more questions about sections 9.1 and 9.2. I already uploaded worksheet number 3, which is a worksheet number 15, which is a compilation of problems from section 9.3. So if you want to go ahead, download it and try to answer the problems. And then let me know what happens on Friday. All right. Bye, everyone. Have a good day.